All right, kia ora. So let's get started on the first task for week number 6 of remote learning. What we're looking at today is just defining how to draw the Lewis structures. So we are now moving on to the next chunk of information for the structure and bonding topic. And that chunk is Lewis structure, shape, and polarity. Cool. So by the end of today's lesson, you should be able to draw Lewis structures and also recognize them as well. So just to kind of recap, before we start talking about Lewis structures and how to draw them, we need to revise when are we going to be using them. We are using them when we are dealing with molecules. And you've already come across molecules when we did our covalent molecular in the types of solid topic. The important thing when it comes to these molecules and in relation to Lewis structure is that we need to think about covalent bonds. So with those covalent bonds, those are valence electrons that are being shared between two atoms, and they exist simultaneously between both of those atoms. These can form between nonmetal elements, so basically anything from 14 to 17 on the periodic table. I really, really like this diagram because it shows you the electron arrangement, but it focuses on the fact that with that electron arrangement, these covalent bonds are just looking at those valence electrons, and those are the only ones that are going to be shared. So those inner electrons are things that we are not going to be concerned about when it comes to Lewis structures. So the first thing to think about is how do we draw Lewis structures, and we'll start with the atom. In this case, all you're doing is drawing the atoms with their number of valence electrons. This is just to, like I said, get us set up on what they look like. Here we go. Hopefully it'll focus once I start writing. All right, so the first one that I have is sodium. Remember, you're going to look at the periodic table and see what group they're in, and that's going to tell you how many valence electrons there are. In this case, it's in group 1, so I only draw the 1 dot to represent that valence electron. You can draw that dot anywhere, and that is fine. So you can draw it there, you can draw it down here, you can draw it on the side. It doesn't matter. The main thing that you're trying to show is that it just has the 1 valence electron. The next example they have is oxygen. So oxygen is in group 14. So we need 4 electrons. You can draw it like that. You can draw it with the electrons paired up. It doesn't really matter so long as you have the right number of electrons. Cool. Last one was is neon. So neon in this case is in group 18. It is a noble gas, and so it's going to have 1, 2, 3, 4, 5, 6, 7, 8. And like I said before, be mindful we are only focusing on that valence shell. We're not concerned about those inner shells of electrons. So even though neon does have the first shell with 2 electrons and then the second shell with 8, making a total of 10 electrons, we are only focusing on those valence electrons because those are the ones that will be shared. Cool. All right. So the next thing then that we need to show is how these atoms get bonded together. So whenever we're showing a bond in a molecule, we can show it either one of 2 ways. We can either show it as 2 dots or we can show it as a dash. Dash means that you're going to have 2 electrons there. Either or is fine with what you're doing. So let me just show you what that would look like. So for example, if I had hydrogen as the molecule, I can either show it as 2 dots like that, joined together. If we're thinking about it as individual atoms, one hydrogen has 1 ion by itself, and the other one has that, so when they come together, they're going to be sharing it. The other option is that you write it with a dash. So that's what that one would look like. I'll just do a little divider so that way you know. So that's the Lewis structure atoms up here. All right, I'll do a couple more examples of it. So the second example that I have is chlorine. So if I was to draw chlorine, remember that chlorine on the periodic table is 7. And what I'll actually do is I'll do this in 2 different colors so you can see what I mean by how there's 2 atoms that come together to make that covalent bond. So that chlorine there has 7. If I was to draw this chlorine, 1, 2, 3, 4, 5, 6, 7, and that location here, that is your shared electrons, aka your covalent bond. So you could show it as this, as one option to how to communicate across. The other option is that you show it with a line. Personally, I like it better with the line because it helps me distinguish between bonded and unbonded electrons, and that's going to be important later when we start doing shapes. The final example that I had was going to be hydrogen with chlorine. So you can draw it like that. Again, I'm just putting it into 2 different colors so you can see where each atom is and where all the electrons are coming from. You obviously don't need to do that on the assessment. It's just to help learn. Or I could also express that as a line like that. And remember that line is representative of 2 electrons. So lots of different choices on how you express that. Cool. All right, I'll keep moving. So the other thing to keep in mind with Lewis structures and molecules is that, get back, there we go. There we go, yeah, next one. So there are a few exceptions to the rule. So if you guys remember when we were dealing with ions, we're trying to get to that full electron shell for that stability. So in most cases, that's going to be 8 electrons. However, there are a couple elements that are stable outside of having 8 electrons. The first example is hydrogen. It only needs 2 electrons to be stable. Beryllium is the next one, which is 4, and boron is the last one, which is 6. So do keep those in mind because that's obviously going to affect some of the Lewis structures that you're going to draw. Because instead of trying to reach the 8, you're trying to reach 6 or 4 or 2 instead. And I'll show you some examples of that. The other thing to keep in mind is that with some of these molecules that we're drawing, they could have double bonds. So in this case, 4 electrons are being shared. You can either show that as, 4 dots, or you can show it as 2 lines, because remember, each line represents 2 electrons. So for example, oxygen would have a double bond. I might actually draw it so you can see it. So oxygen would be shown like that, or you can show it like that. Also keep in mind that you can move the electrons around. They don't need to be in those positions. You could also do something like this and have the electrons like that. It still all means the same thing. So that's how I would express double bonds. You could also have triple bonds. So if we're looking back at the notes, triple bonds are when 6 electrons are being shared. You can either show that as 3 sets of dots or 3 lines. So for example, if I had nitrogen, I can do it like that. And I'll explain how I know how many electrons to put down later in this lesson. So you could show it like that. You could show it like this. And that's fine. You could also show it like that. And like I said, you can move those electrons around. They don't necessarily need to be on the top, so long as you have the right number of electrons there. So that's how I'd represent triple bonds. Again, I prefer the lines because the lines make it very clear on what's bonded and what's not bonded. But either way will be fine. All right, cool. So the next thing we then need to think about is how do we draw Lewis structures and the rules for doing that. Now there's 2 methods for us and how to do that. I'll do several different examples, and I'll do each example with each of the methods so you can see it. And in fact, what I will do is I will do 3 different molecules so you can see the comparison and just get a lot of practice. And that way you can also see things that have, multiple bonds, and what's the other word I want? Multiple bonds, and exceptions to the rules. So I'm just folding a piece of paper right now so I can divide it up so you can see it into 3s. Cool. So I'll show you method number 1 first. So method number 1 I like to call as the mathematical method. Let's switch over to the document camera. Cool. So method 1, I'll show you a few times. I'm really sorry about that light in the document camera. I wonder if I can... No, it's gonna have to just live with it. All right, with method number 1, I'll show you 3 examples. We will do CH3, not CH3, CH4. We will do oxygen, and we will also, actually no, let's do carbon dioxide. And then the last one we'll do is BH3, so that way you can see some different examples. All right, so the first step with this method, whenever we're looking at trying to do this, is we need to determine the number of valence electrons for each atom involved. So I'll go through one example. So with CH3, we're going to go through and look at the periodic table. Carbon is in group 14, so it has 4 valence electrons. I think I made a mistake somewhere when I did oxygen. Oxygen is in group 16. My bad. There you go. Fix that. All right. So carbon has 4. Hydrogen only has 1 valence electron. It's in group 1. Now what I need to do next then is multiply by the number of atoms that are involved in that formula. So in this formula here, I only have the 1 carbon, whereas in this case, I have 4 hydrogens. So 4 times 1 is 4, 1 times 4 is 4. Total electrons that I'm working with are then 8. That's really important to know what I'm working with, because then I need to think about what do I need in order for stability. So step number 2 is calculate the total number of elements if they were to have 8 electrons. Be mindful of any exceptions to the rule. So carbon would have 8. Hydrogen would have 2 in order to be stable. So do keep that in mind, that it's an exception to the rule. Times it by the number of atoms you have of each. So I have 8 and I have 8, so I have a total of 16. So I need 16 electrons for all these atoms to be stable, but I only have 18 to work with. So now we use that mathematical method to figure out how many of these electrons are being shared and how many bonds we have. So what I'm going to do is I'm going to take what I have did in that first step and that second step. So we're going to take the second step and subtract it from the first. So I'm taking, this is B, that was A, and we're doing B minus A. So 16 minus 8, 8 electrons are shared. Now I know that each bond must have 2 electrons, so if I do 8 divided by 2, what that tells me is that I have 4 bonds in this molecule. All right, so now that I know that, what I want to do is start with the drawing. In this case, I'm going to need to figure out what's the center atom. Several different ways you can figure that out. First off, you can look to see which one has somewhere between 3 to 5 electrons, because then they can do the most bonds possible. The other thing is you look for repeatedness of it, because stuff that's being repeated is going to be branched on the outside, and stuff that is unique will be in the center most commonly. Cool. So let us draw that out. So carbon's going to be my central atom. And then I have the 4 hydrogens around it. I have 4 bonds. So I'm going to put 1 to each hydrogen, and that accounts for the 4 bonds that I have. The other thing I can double check is, do I have the right number of electrons? I have 2, 4, 6, 8. So I do have the 8 that I originally had. And then the last thing I do is just double check to make sure everyone has filled the octet. Sorry. First off, I check if there's 8, and there is, so I don't have any extra electrons to put down. And then last thing I need to do is check to make sure everyone has their full. So carbon has 8 because that's what it needs for its full stability. Hydrogen, on the other hand, only needs 2, which it does have with those single bonds. So that's the first example. Next example, let's do carbon dioxide. So carbon, like I said, is 4. We only have 1. So that gives me 4 electrons. Oxygen has 6 valence electrons. I have 2 of them. So that gives me 12. So I'm working with a total of 16 electrons. When it comes to how many electrons that I need, both of these guys need 8. That one's times 1. That one's times 2. So I have 16. I have 8. And then total, I have 24 electrons that I need for that one to work. All right, now it's time for that subtraction step. 24 minus the 16 that I have. What is that? 8. Yeah, 0. Cool. So I have 8 shared electrons. And remember, basically what we're doing with this is that we're sharing electrons so that way we have enough electrons to go around, because we can't just create matter out of nowhere. So if I divide that by 2, I have 4 bonds. Again, let's figure out what my central atom is. So in this case, it is going to be that carbon. It's the only one there, and on top of that, it is got more ability to bond because I have 4 empty spaces, whereas oxygen only has 2 empty spaces to get to the 8. Now I know that there's 4 bonds there, so there must be 2 between each carbon and oxygen. So I have my 4 bonds. If I'm checking the number of electrons that I have 2, 4, 6, 8. So I only have 8 there. So I have a remainder of 8 electrons left. So since I have 8 electrons left, I now need to start putting them down. And we put them down starting from the outside going in, making sure everyone has the octet, or whatever number they're supposed to get if they're an exception. So 1, 2, 3, 4, 5, 6, 7, 8. So that's how I know where those electrons go. Again, double check, does everyone have 8? 2, 4, 6, 8. Oxygen's fine. 2, 4, 6, 8. Carbon's fine. 2, 4, 6, 8. Oxygen's fine again. So that is another example. All right, last one that we'll do is, this one's an exception to the rule with boron. So boron is in, ooh, I gotta look. Let's check that periodic table. Boron has, what are you? Oh, I need a periodic table. Boron's in group 13, so it's going to have 3. So 3 valence electrons, there's only one of them, that's 3. Hydrogen has 1 valence electron, and I have 3 of them. So total electrons that I'm working with is 6. All right, next step is to figure out how many I need to be stable. So remember how I said boron is an exception to the rule? If we don't remember which number that is, we can look here. So beryllium is 4, boron is happy with 6. So we're going to use that number instead of 8. And then hydrogen is also an exception to the rule. It only needs 2. So I need 12 electrons in order for everyone to be stable. Remember, it's really important to keep a running total of the electrons that you have, especially with that 6 here, because you can't create or destroy matter. All right, so 12 minus 6 equals 6 shared electrons. If I divide that by 2, I will have 3 bonds. So let's draw out that molecule. So I should be drawing 3 bonds, and then let's double check. So I have 2, 4, 6. That matches with the number of electrons that I have to work with. It also matches with the 3 bonds. And then double check to make sure everyone's stable. That one has 2, that one has 2, that one has 2, and that one has 2, 4, 6. So they're all fine. So just watch out for those exceptions. So those are 3 examples with method number 1. That is the mathematical method. Here is method number 2, which I like to call the guess and check. Method number 2, I think, is more useful long term because you'll use it in level 3 chemistry. So if you have no preference, I would say do method number 2 because it'll help you in the long run. And we'll do the exact same things again, so you can see the difference between the 2. All right, similar first step when it comes to how we go through it. The first step is going to be count the number of valence electrons. So we've already done this in the previous one. I'll just copy the numbers over. So this has 8 valence electrons. That one had 16. And that one had 6. So that's just step number 1, how many valence electrons. And I'm just copying it down because we've previously figured it out in the last one. I'll just shift over. I might do carbon dioxide first because you can see the steps better with carbon dioxide. All right, cool. Next thing then is I place the center atom down. So again, we're just using that knowledge of which one can do the most bonds, which one is kind of unique. So I'll do carbon dioxide first, so that way you can see the method better. So what I've done is I've placed the carbon and the 2 oxygens down. I've assumed carbon's in the center. And then next step is to connect all the atoms, and you need to connect them with a single bond because we are assuming in this case that everybody needs at least 1 bond, so that way they're all connected together. Now what you need to do with this method is you need to keep a running total of how many electrons you've used, so that way you know how many you're still working with. So I have used 2, 4. So I'm going from 16 now down to 12 electrons left over. With those 12 electrons, I'm going to start placing them in the outside atoms first, going inward. So since I have 12, we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I've placed those down. So now I've used up all my electrons, and I need to double check if I have full shells. So I look over here, 2, 4, 6, 8. Oxygen's fine. 2, 4. So that's an issue because there's only 4 there and we need to have 8. 2, 4, 6, 8. That one's fine as well. So in this instance, this Lewis structure is not correct because my carbon doesn't have enough electrons. So now what I need to do is I need to start moving my lone pairs of electrons inward to form a double bond. So I will take these 2 here and I will form a double bond, and now my carbon number has gone up to 6. So we're getting closer. Doesn't matter which electrons you take off. I'm just taking the ones off the side, but you cannot, like, obviously erase the ones on the top, and that's fine too. So if I want, I can erase those two, move it into a double bond. Those 2 electrons are still with the oxygen, so that doesn't actually change it. But now this guy has gone up to 8, and it is okay. So basically, I call this the check and guess method, or the check and move method, because you are starting the setup and then you are shifting electrons around based off if it has the full shell or not. If I had any extra electrons, I would go outside going in, and so any extra stuff goes in the center. I might give you a third example just to show you that. All right, so here's this is the methane. Leave that. Assume that everyone has to have 1 bond. Check if everyone's okay. Hydrogen has 2, 2, 2, 2. Carbon has 2, 4, 6, 8. So we're done. So that's a nice easy one to then do, because you don't have to worry about moving anything around. Let's check this one over here. So assume B's in the center, boron's in the center. The hydrogens are around it, assuming you have to have at least 1 bond between those hydrogens. Check to see if I've used and I have any leftover electrons, 2, 4, 6. So I have my 6. Check to make sure everyone's stable. That one has 2, that one has 2, that one has 2. And I know boron is happy with 6, 2, 4, 6. So we're all fine. I'll show you one more example because I think it's useful with this method, and that's just to show you what to do with lone pairs. So if I have ammonia, nitrogen's in group 15, so that gives me 5. Hydrogen's in group 1, and I have 3 of those. So if I'm adding those together, I have a total of 8 electrons that I'm working with. Nitrogen will go in the center, and then the hydrogen's on the outside. Assume everyone has to get connected with 1. So 2, 4, 6. So I've used 6 electrons, and I still have 2 more. Now with those 2 electrons, remember we're going outside in. So if I check hydrogens, all the hydrogens have 2, so they're stable, so I don't need to put any electrons there. And the last 2 electrons will go onto the nitrogen. Again, is nitrogen now stable? 2, 4, 6, 8? Yes, it is. So that's what we're doing with that method. Both methods work. Method 2 is better for preparing you for chemistry next year, but if you prefer method 1, you are welcome to use that. Cool. All right, hopefully that makes sense. So that is Lewis structures. The main thing about Lewis structures is practice, practice, practice. So by the end of today, you should be able to draw the Lewis structures. Like I said, do lots of practice with it. It is on the Mahi Choice. Resources are on the Google Classroom. Basically, you just need to take your time and practice it. Eventually, you'll get really fast at it, and you won't need to do the step-by-step process of counting the electrons and doing the guess and check and move. You'll get kind of like a sixth sense for what they look like. But do be careful not to rush them, because in our next lesson, when we have to determine shape, we are determining that shape off of the Lewis structure. So if you get that Lewis structure wrong, it's going to snowball and affect your shape and thus your full justification. So do take your time to learn how to do this properly.